All right, so we are doing the last part today where we're going to talk about focusing just on groups 1 and 17. And we're going to look at mostly at their chemical properties. We are going to talk about a couple of physical properties like melting point as well and density. But mostly it's going to be chemical properties. The reason that we talk about these two groups kind of individually in a little bit more detail is because group 1 metals, these are our alkali metals like sodium and potassium and lithium. So they're the most reactive metals. And group 17 are the halogens, which are like chlorine and fluorine and bromine. They're the most reactive nonmetals. So because these are the most reactive groups on the table, group 1 being the most reactive metals, group 17 being the most reactive nonmetals, we see them in a lot of different chemical reactions. We see them doing a lot of different things in a lot of different compounds. And so we tend to like use them more. And so it's good to know about their properties more because of that. Okay. So chemical properties are determined by electrons because remember, chemical properties have to do with breaking and making bonds, which means that our electrons are going to be either transferred or shared and bonds are going to be formed or broken. And so that's what it's kind of saying here. It's determined by its electron configuration because the number of valence electrons are going to determine how it's going to react. Okay. And so based on that, elements that have the same number of valence electrons, they tend to react the same way. So because of that, if they are in the same group, they have similar chemical properties because they have the same number of valence electrons. Okay, so things like oxygen and sulfur, they both have 6 valence electrons. And so because they have 2 single electrons and 2 pairs, they're usually going to make like 2 chemical bonds. Okay, and that means they can also make a double bond. All right. Things like carbon and silicon that are in group 14, they have 4 valence electrons. They're all single, so they can make 4 bonds. That's why they do that like giant covalent structure that we talked about last time. So group 1, alkali metals. First off, like I said, they're the very reactive metals. They're the most reactive metals on the periodic table, okay, compared to all of the other groups of metals. So some physical properties they have, they're shiny when you cut them, but very quickly they react with oxygen in the air. And so the shininess kind of goes away and they're covered with a layer of oxide. So like if I had a piece of sodium, and all the alkali metals are very, very soft, which I don't think it says that on here, but they're very soft. Like you can cut them with like a plastic knife or a butter knife. Okay. You don't need like a sharp knife or like a saw or anything or like a laser. You don't need any of that to cut alkali metals. They're very, very soft. And so when you cut through them, right at the beginning, you'll see the shiny, kind of silvery gray color where it reflects light. But pretty quickly, you see it get covered with a layer of kind of like a whitish color, usually maybe a whitish gray, depending on which element you have. And that's because the oxygen from the air is reacting with that metal. So if you had sodium and you cut it, that layer of sodium oxide is forming on the outside. If you had potassium and you cut it, a layer of potassium oxide is going to form on the outside. And so when you look at a piece of it, sometimes it doesn't look like a metal because you're like, it looks really dull. It's not shiny, but that's because that outer layer is all been exposed to air. If you cut it and look in the middle of it, you'll see it is shiny. It's just, it doesn't last very long because it's that reactive. It's so reactive that at room temperature, it's going to react with oxygen in the air and form some kind of oxide, sodium oxide, lithium oxide, etc. So because of that, all alkali metals, they're all stored in oil. We have a couple here at school. They're all pretty dangerous. So we're not allowed to have certain ones of them. Like we're not allowed to have potassium anymore. We're definitely not allowed to have rubidium and cesium because they're extra reactive. But we do usually keep lithium and sodium samples here, but they are stored in glass jars in oil, like completely covered inside of a flammable cabinet. Okay, because they're so reactive that we have to take like extra precautions. And when we do use them, students are never allowed to use them. It's always like the teacher, I might like show a demo of it or, something like that. But you guys are unfortunately never allowed to handle it because it's so dangerous that even little pieces of it, because it'll react with water and it explodes. Okay. So some of them, lithium and sodium aren't as reactive, and so they'll just kind of light on fire. But like potassium, rubidium, cesium, they will explode when they get into the water. Okay. Um, the first three, they have very, very low density. So this is a physical property, density. They actually float on water. Okay. So lithium, sodium, potassium, their densities are less than 1. So they float on water. The other ones, they won't necessarily float. Um, they have low melting points. Okay. This is another physical property. So they have low melting points because they're metals. Okay. Compared to like the um, melting point of like, carbon and silicon, where they were really, really high last class. But then we also need to understand that within the group, even though the melting points in general are low, as you go down the group, the melting point gets even lower, because as you go down, your atoms are getting larger. So your metallic bond is getting weaker since your valence electrons are further away from the nucleus. And that causes the melting point to decrease. So it's going to be easier for you to change it from a solid to a liquid as you go down. And then we've talked about this in the past, that they lose their one valence electron and they form positive ions with a +1 charge. And so for reactivity, the reactivity increases going down the group. So you kind of heard me kind of hint to this earlier, where I said like we're allowed to keep lithium and sodium stored here on campus because while they are very, very reactive, they're not as dangerous as the rest of them. We are not allowed to have any of these on campus. In fact, I found some potassium in a storeroom last year, and then when I told somebody, when we told somebody about it, they were like, wow, I can't believe you have that. Like, you're not supposed to have that on campus anymore. And like, so we had to go through a process and get rid of it and all that stuff safely. So somebody who taught here a long time ago, I guess, had it, and then they didn't get rid of it when they changed the rules and told us like, we're not allowed to have it anymore. So the reason that the other ones like potassium and lower are we're not allowed to have them is because they are highly reactive, like so reactive that their danger of them outweighs like the benefit of like having them here to like use them and show you guys anything. Lithium and sodium, they're still pretty dangerous. They're still going to catch on fire in water. They're still going to react really easily, but not as much as the other ones. Okay. And the reason that the ones further down the group react more is because atomic radius increases. And so less energy is required to remove the outer electron. So it connects back to all of our other trends, okay? As you go down, you're adding energy levels, which makes your atomic radius increase. That means your valence electrons are farther away from the nucleus, so they are not feeling the pull of the nucleus or the attraction of the nucleus. The nuclear charge is a lot lower down there, and there's increased shielding. And so because of all that, because the electrons are further away and there's more shielding, it requires less energy. So the ionization energy is lower. So it's really easy for me to take an electron from like francium or cesium. Lithium, it's still fairly easy to take it, but not as easy as the other ones further down. And so the more easily it loses that electron, the more reactive it is. So that's kind of explaining the reactivity for the alkali metals in terms of their ionization energy and the ease of removing an electron. Now, specifically, I mentioned that they react with water really, really easily. Okay. So we need to know, well, when they react with water, what's happening? Well, when they react with water, they form hydrogen gas and a metal hydroxide. So it could be like lithium hydroxide or sodium hydroxide, whichever alkali metal it is, it'll be that metal and then hydroxide, OH. And we talked about that they're basic. So here's the pH. The solution is alkaline. Alkaline is another word for basic. So that goes back to our acid base character from last class. So if I were to drop a piece of lithium in water, so here's solid lithium, if I dropped it in some liquid water, it's going to produce lithium hydroxide, which will be an aqueous solution, and it'll give off hydrogen gas. Hydrogen gas is highly, highly flammable. So that's why you see sort of a fire or like a flame or sparks when you have alkali metals on water, because they all produce hydrogen gas, which is flammable. Okay. And so in general, this is what the pattern would look like. And so I could substitute instead of lithium here, I could substitute sodium and I'd get sodium hydroxide. Okay. I could substitute potassium and get potassium hydroxide. So the pattern would be the same. The metal would be the only thing that would change. Okay. All right. All right, group 17, these are the halogens. So now we're talking about the most reactive nonmetals. Halogens are also called salt formers. It's kind of like a nickname. The reason they're called that is because when they react with group alkali metals, they form salt. So think of like sodium is a group 1 metal, chlorine is a halogen. So when chlorine reacts with sodium, it makes sodium chloride. That's table salt. And the other ones, you know, if I had fluorine and it reacts with lithium, lithium fluoride, that's a salt. All ionic compounds where you have a metal and a non-metal are salts. And so that's kind of why they're called this nickname. They're called salt formers because of that. They're the most reactive non-metal elements, as I mentioned earlier. One unique thing that you need to know, the halogens in general, except for fluorine, but the other ones, they're all different colors. Okay. And so you can use color change as a way to see like a chemical reaction happening, because if I have, you know, something that's colorless and all of a sudden I see a gas form and the gas is like a yellowy green color, I need to be concerned, because that means that chlorine gas is being produced, and chlorine gas is poisonous because chlorine gas, it wants to gain electrons, and so it will react with anything it can to steal an electron. All of these elements will, but chlorine and fluorine more than the other two. And so what happens is if you breathe in chlorine gas, it reacts with the water and oxygen in your lungs, and it takes electrons from them and it suffocates you. It was used in World War I as a chemical weapon. And then I'm not sure the exact dates, but at some point after World War I, it was outlawed with like the Geneva Convention, because it's a form of chemical warfare, and that is not something that, you know, is ethical or moral. And so, but it was used in World War I. So it's sometimes called mustard gas because of kind of like the color of it was this yellowy green color. So mustard gas, chlorine gas, those are kind of the same things. Bromine, on the other hand, it's a liquid, and it's got a reddish brown color. So it's a reddish brown liquid. Iodine is a solid, and it's actually a purpley color. It's kind of almost looks black. It's like a really dark purple. And so all of them have their own unique color. And notice they're all different states. Like chlorine's a gas, bromine's a liquid, iodine's a solid. And the reason that they change from in states down the group, the reason they're not like all gases or all solids or something like that, is because of some of their properties. This is what the next bullet kind of says. It says that they show a change. So the first two at the top, they're gases. Then you get to bromine, that's a liquid, and then iodine is a solid. And then astatine, we don't really talk about that one too much because that's one of the ones that was discovered a lot later. So it doesn't really do a lot. But the top four, you have two gases and then a solid and then a liquid. What happens is the molar mass is increasing because our atoms are getting larger. And when you have larger atoms, they have more of these things called intermolecular forces that we're going to learn about a lot more when we get to topic 4 and we talk about bonding. But because fluorine and chlorine don't have as much of those forces, they're a gas, and it doesn't take much to change them from like a liquid to a gas. Bromine has a little bit more of those forces, and so it stays a liquid at room temperature. And then iodine, because it's the largest, it has the most of that force, and so it stays solid at room temperature. Okay. All of the halogens are diatomic, meaning that, you know, they're all like F2, okay, like their formulas here. So naturally occurring, they're never in a single atom. They're the opposite reactivity as the group 1 metal. So on these, reactivity decreases going down the group, okay? And the reason it decreases is because, again, atomic radius is increasing, more energy levels they're occupied. And so the attraction for the electron decreases, because the difference here, the alkali metals are more reactive as you go down because metals want to lose electrons. So bigger atoms lose electrons more easily. So as you go down alkali metals, they're more reactive. These are the opposite. Non-metals like halogens, they want to gain electrons. So if I go down the group and the atom's getting larger, that means that it's not wanting to gain an electron as easily, because the larger atoms lose electrons. They don't gain them. And so because at the bottom, things like iodine are going to be larger, they're going to be less reactive. Fluorine is the most reactive element. Okay. All right, last one is these two reacting together, group 1 metals and halogens. We should kind of understand the basics. When a halogen reacts with a group 1 metal, they form an ionic compound, okay? The alkali metal has a +1 charge. The halogen ion, or they call it a halide ion because the ending changes, becomes negatively charged. And so both of them end up stable because they both end up with the electron configuration of a noble gas, because the group 1, the alkali metal, gives its 1 valence electron away, and the halogen takes that valence electron and it fills its outer shell. Okay. And so in general, this is typically what their equation looks like. You have to have 2 of the alkali metals because your halogens are always diatomic, so they're always going to have a 2 subscript. And then you'll make your formula will not have any subscripts because everything's +1 -1. So it might be like NaCl, or it might be like NaF, or it could be like KBr. Okay, it just depends on which ones you're putting together. But all the ionic compounds, they'll all be solid. Okay. And then you have to balance it. So that's why there's a 2 here and a 2 here. Okay. But they're going to follow that same general pattern of, metal plus, or group 1 metal plus halogen, and the halogen is diatomic, makes your ionic compound that is solid. And then you'll usually have to put a 2 in front of your alkali metal and a 2 in front of your ionic compound on the product side, just to make sure that it's balanced. Okay. And so because both of these are the most reactive, these compounds are formed really easily because sodium and chloride, or like lithium and bromine, or all, whatever combination, they all really want to react to become stable. Okay. So